I watched a camel eat a cactus today. I mean, not in person, but on YouTube. Camels are adapted to their desert environment so they can eat cacti. And some of the cacti that have 6-inch spines on them, which is longer than this, so they can eat cacti just straight into their mouths. And they can do that because if you look up a picture of a camel's mouth like this, you see that the insides of their mouths are nightmare shows. They have, they're just ringed with what's called papillae, or papillae, if you're nasty. And those are kind of like little fleshy bumps all the way inside of their mouth and all the way down their throat that kind of protect the mouth tissue and allows them to eat spiny things. But it makes their mouth look like a sarlacc pit, more or less. And do you know who hates sarlacc pits? Han Solo! Segway, baby! Hello and welcome to another episode of Because Science Footnotes, the show, the show where I take your nerdy comments and questions looking back on all the previous nerdy stuff that we got up to on this channel, and then we look forward to what's going to be happening on the next stuff that's on this channel. It's kind of like a seesaw with you on one side and me on the other. But if there were like 50 or 100,000 of you on one side of a seesaw and you all jumped on the seesaw at once from like a height of a meter, I would be launched into the air with the kinetic energy of a car at highway speeds. Sounds fun. I've always wanted to be on a highway. Life is Nope. On the last episode of Because Science, I said that Han Solo, yes, that Han Solo, is wrong about hyperspace. More specifically, I was looking into the accuracy of a 40-year-old quote from A New Hope, where Han Solo says, if you don't have precise calculations and you make the jump to hyperspace, you might end up flying through a star or bouncing too close to a supernova, and that would end your trip real quick, wouldn't it? Well, would it? I said that because of how big space is and how far apart stars are, if you're worried about hitting something like a star-sized thing, then in fact, you could make a completely random jump to hyperspace and never hit anything. Thousands of times, you could cross the galaxy, even cross the entire universe thousands of times over without ever hitting anything, on average. So I said Han Solo was wrong about that. But what did you say? Boop, right on your nose. Well, we have a bunch of questions for this episode, but I'm going to take them lightning round style and try to get it done in less than 12 parsecs. To start our comments off, as usual, Matterbeam has he, she, they's giant list of all the things that I wish I could always think about, but I can't. A lot of calculations, a lot of interestingness. It's basically calculating how fast you can go before you vaporize your spaceship, because there's always something in space. Even though space is very empty, there's lonely atoms and photons around, and the faster you go, the more of them hit you at higher velocity, which means the more energy transferred to your ship or your shields or your armor or whatever, and then you get hot and then you die. So go to the YouTube page and check out Matterbeam's comment as usual. Our first real comment comes from Kyle Westbrook and Iron Andrew. I almost said Iron and Rue. Who say, okay, star-sized stuff have a pretty low chance of hitting it, but what about the chances of hitting planets or things smaller than suns in the Star Wars universe? Well, I didn't consider planets or other spaceships in my calculations because planets are so much smaller than stars, even though there are a lot of planets in galaxies, hundreds of billions, possibly in hundreds of billions of galaxies. But for example, the radius of the sun is 100 times the radius of the Earth. And when we do these free mean path equations, what we are worried about is the cross-sectional area of running into something. So for the sun, it's pi times the radius of the sun squared that gives you the cross-sectional area that you don't want to hit. The Earth has a radius 100 times smaller, which means, because the r is squared, that the cross-sectional area of something like Earth is 10,000 times less than something like the sun, which means it's going to be a lot harder to hit, even if there are a lot of planets. 1 million Earths could fit inside the volume of the sun, to give you an idea of how small the Earth is in comparison to stars. So stars are a much, much bigger worry, and because Han Solo referenced stars and the death of stars specifically, that's what I went with. Next comment comes from just someone here who says, never think I would imagine a volume of space as a giant salami. Thanks, Kyle. You're welcome. I've seen a lot of physicists use like loaves of bread to visualize space-time, but that's boring. Give me that space meat. Our next comment comes from Matthew Robson, IX Radioactive XI, among others, who say something about, ooh, it's so cold that you leave out Pluto from the list of planets. Look, nerds, all right? Pluto is gorgeous and fascinating, and we should explore it, and yes, it has a lot going for it, but it is technically not a planet. Do you want to be cool or do you want to be correct? That explains a lot of my life. Our next comment comes from Obi-Wan Kenobi. General Kenobi? Haven't heard that name in a long time. Do you mean old Ben Kenobi? Another happy comment. I just want to acknowledge his name. I don't even want to read what you said. Our next comment comes from a sad, strange little man who says, would you drink a glass of alien milk like Luke for $10,000? Nope. Imagine what could be in it. We're smarter than this. Our next comment comes from Harrison Tarabella, who says, so with faster than light travel stuff, if you're on a ship moving faster than light, then how can you see? So I did an episode about how hyperspace might really look like before, and I want to actually add something to it because I found something really cool in a paper. In my episode, I said that wavelengths of light that you normally can't see, like the cosmic microwave background radiation, would blue shift up into visible light. Kind of like how when something gets really hot, it goes from infrared light up into visible light. That's why it's called red hot. That's what's happening there. But I found a paper that actually shows, bing, what space around you would look like as you travel closer and closer to the speed of light. And if you look at that, it is like a tunnel of kaleidoscopic rainbow-like colors. It's almost like that tunnel that those kids go through in Willy Wonka. And there's no earthly way of knowing all the colors space would be showing. Oh wait, there is science. Our next comment comes from VlogBit, who says, can you explain hyperspace and basically how it ignores relativity? That's why we want something like hyperspace, VlogBit, is because it gets around relativity. Specifically time dilation, I think, would be the biggest problem, because if Han Solo just made one Kessel Run, 12 parsecs or around 40 light years, and he came back, by the time he came back, if he was going near the speed of light, he wouldn't have aged that much. But everyone else in the galaxy would be almost 80 years older, which means when he came back to Tatooine, when he sat down with Ben Kenobi, he would be canonically older than Ben Kenobi, which is weird. And both Death Stars would be gone. Weird stuff happens when you go fast. But my favorite comment this week at the time of this filming comes from the Atheist Paladin, who says, this pretty much proves the opposite of what Han Solo said. If you want to get anywhere, you have to make a price calculation, or else you just end up in some empty void out of the middle of nowhere. You're right. Space is so big that it's almost the exact opposite. You would have to be very deliberate in where you want to go, or else you would end up literally nowhere. So congratulations, the Atheist Paladin. You are a super nerd. Wow! But you are a terrible grammarist. Out of the middle of nowhere with a price calculation. Get out of here! But of course, I'm not always correct. I'm not. So what did I get wrong this week? By far, what most commenters had a correction for is the effect of gravity and gravity wells on hyperspace. So apparently in the Star Wars universe, gravity wells affect hyperspace travel. So this correction gets really complicated. It's assuming that not only is hyperspace a real thing, but gravity can pull you out of it, okay. But how close do you need to be to the gravity well, and how much gravity does there need to be? Let me put this into perspective for you. Gravity acts under the inverse square law. So a point source of gravity, the further you get away from it, there's like an expanding shell of surface area if you imagine that shell, and the farther that you get away, the more that shell spreads out like a balloon inflating, and the less gravitational field strength there will be. So for example, if you have a point source of gravity like the Earth, which has a gravity well, but you get 10 radii of Earth away from the center of the Earth, the gravitational field strength will have decreased to 1% of its value. So if we use something like 1% of gravitational field strength, saying, oh, that's far enough away from a gravity well, then it increases the size of our cross-sectional areas that we don't want to hit for planets and stars by 100 times. But in our equation, in the episode, I increased the radius of the stars that we're concerned about by 2,000 times, bigger than any known star, and it still allowed for almost blind travel unimpeded by any smashing through of plasma. So I still don't think the gravity well correction is a real problem, because gravity wells reduce themselves according to the inverse square law, and you do not have to get very far away from those wells to not experience their full strength. Of course, if you had a Star Wars interdictor ship or whatever, and you projected gravity somehow, or you induced gravity around a ship somehow, then you could mess with that ship. But stars don't do that. Neither does the universe. Our next correction comes from Tyler Smith and Smokescale, Aquatos, and David Hewitt, who say some version of, well, hyperspace is more like traveling into a different dimension, and so it's kind of like teleporting. You jump to hyperspace, cross a small amount of distance, you cross the distance you want to travel in a different dimension, then you pop back into this galaxy or wherever. So it is more like teleportation. And they say, well, then wouldn't you have to be very precise for where you wanted to go? I still disagree. If traveling through hyperspace is like teleportation, imagine how much less volume you are traveling through. So in our calculations, we were considering moving through a volume that kind of looks like this. If we were moving through space, and it was filled with stars, what would be the chance that we'd run into a star? How far could we go before we hit anything? But if you were traveling through hyperspace like this, going boop, boop, you are avoiding traveling through all of this space. And then the question is, what are the chances that you would randomly appear in a random section of space and be inside the volume of some matter? That is way, 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 way lower than what we calculated. So still effectively 0 chances of running through a star if it's random, completely. Our next correction comes from Jake, who says, does the free mean path take into consideration the size of the traveling particle? It looked like the formula that you used assumed the particles to be identical, so it's like making the Millennium Falcon the size of a star. So you're on the right track here, but it's a little bit different. So in normal free mean path calculations, you are calculating the distance that a particle can go before it impacts another particle. And usually you use the diameter of that particle squared, because the area that you can hit something is the entire area of this particle and all the entire area of this particle, because they can just touch each other on the edges, and that's still a collision. But for a ship, like a spaceship and a star, the star is so much bigger. Remember, 1 million Earths can fit inside the volume of the sun. And a spaceship is smaller than the Earth, I think. So when considering the cross-sectional area of stuff that you don't want to hit, you can basically ignore the cross-sectional area of the ship because the star is so much bigger. So no, the Millennium Falcon in our calculations wasn't star-sized. That'd be pretty awesome. But the star is what we're concerned about. But my favorite correction at the time of this filming comes from Trainer JB, who says the chances of shutting down a whiny know-it-all teen by telling him you will hit a star if you don't get calculations from the nav computer equal 100%. So there's a lot of nerdy comments, a lot of great discussions, a lot of numbers being thrown around in the comments, but I love corrections like this because it's something I wasn't even thinking about. What if Han Solo was just yelling at Luke to get him to shut up? And he knew that space is big. He's like, oh, come on, you gotta do the lever, you gotta jump to hyperspace. He's like, no, well, if you don't shut up, we're gonna be inside of a star and die. Which is kind of like the parents' version of, we'll get there when we get there, shut up. Which I like. What if he was doing that? I mean, it wouldn't be the weirdest retcon that fans have done to make Star Wars as a universe work scientifically. So, congratulations, Trainer JB. You are indeed a super nerd. Kratos. Stories are for the boat boy. We're getting there. Now, if you are subscribed to Alpha at projectalpha.com, you already know what the next episode of Because Science is going to be because you have already seen it. But if you haven't subscribed yet for premium content and this show, not this one, but the main one, 2 days earlier than anyone else, the next episode of Because Science is Never Land Like a Superhero. I'm serious. That's right. In this week's episode of Because Science, I am listening to Deadpool and trying to prove him right by saying that yes, the superhero landing is almost designed to break you, and it is completely impractical to do so. And trust me, I show you by doing it myself from a pretty serious height. And my thighs are only now better. It's been a week. And stuff gets thrown at me in that episode, so stay tuned. So go watch the last episode of Because Science if you haven't yet, all about Han Solo and hyperspace, and leave your best comments, corrections, and questions at youtube.com/BecauseScience, facebook.com/BecauseScience, and at Because Science on Instagram and Twitter. And that's where I'll be pulling them from for this show. I already said that. Also, someone, user DaveFace, took it upon his or her or their self to create a subreddit for all things Because Science and me. reddit.com/r/Kyle Hill, and it's already pretty filled out. It has a header and image and everything in most of the videos. So if you want to go subscribe there and start having discussions there as well, I'll be popping in and checking it out. So get there and get nerdy. And don't forget, I forgot. See you next week. Oh, it's not even open. I forget a lot of things.